This is a tiny robot that my friend Carl built. My mission is to build an app to control it. It all started out as a simple joystick, but very quickly it turned into a 2-year project. This is everything I learned building an app for an ESP32 robot. I will walk you through every step, from figuring out how to connect and control the robot, to building a way to update its firmware wirelessly, to hiding all the cool tech behind cool animations that ended up taking more time than the actual controller. This is the robot that my app needs to control. It's designed for makers, it has 4 motors, a LiPo battery, and is controlled by an Arduino compatible ESP32. Apart from this, the app also needs to control other devices like this code cell. Supporting multiple devices made everything way more trickier, but I will show you how I tackled it. To handle multiple robots, the app needed to have 4 main features. Device organization, so you can add multiple robots and even name them. Bluetooth scanning to scan for devices, recognize supported devices, and establish a connection. The actual user interface to control the robot, and it has to provide wireless firmware updates to all devices. But before going into that, I had to decide how the app should connect to the robot. The ESP32 board supports Wi-Fi and Bluetooth low energy. With Wi-Fi we can have a longer range and it provides better performance, but the downsides are that it uses more energy and the mobile ends up without internet since it's being used to connect to the robot. Bluetooth, on the other hand, allows the internet to remain active. It uses less power but will give us less range. Apart from these 2 options, I also considered other options like connecting the robot to the home internet. This would allow the mobile device to keep connected to the internet, but implementing this is hard. For starters, it would have required a server to keep running all the time, which would have added high monthly costs. Apart from this, this option would have added a lot of network delays, which would have made controlling the robot very difficult. The only disadvantage of Bluetooth was the short range, so I decided to do a range test to determine if this would be a problem. To my surprise, the robot remained connected up to about 40 meters. This is more than enough for most use cases. If you have never worked with Bluetooth low energy, it works something like this. It essentially abstracts the data transfer to empty boxes called characteristics. These characteristics can be grouped in services. Whatever you put in a characteristic will be synced between the robot and the mobile app. Bluetooth Low Energy can also give you a notification to indicate that a characteristic has changed. As I explain this concept, it might sound easy, but when you remember that we need to control multiple devices, each with their different characteristics and logic, things get complex very quickly. Additionally, the app needs to be future-proofed to support future robots and devices that Carl might release. When dealing with a problem like this, code organization is super important. In projects like this, I spend more time finding ways to improve the organization of the code than actually coding. Coding, especially now with AI, is easy, but building an app that can scale is future-proof and maintainable is not as easy. This project in total took 2 years. Most of the time I forget what I coded 2 weeks ago, so 2 years is a very long time to remember what you have coded. But I have a trick that I always use in all of my projects to keep a project familiar even after 2 years. The secret is using the same code architecture in all of my projects. In my case, I try to use MVVM for the presentation layer of the app and a repository pattern for the data flow. If you want to know more about code organization, subscribe, because I will be making more videos on this topic. Initially, I was communicating to the robot using this basic flowchart, but everything became messy very quickly. So I decided to divide the Bluetooth stack into multiple layers. Each layer only communicates to the layer over it and under it. This made it a lot easier to add any number of different devices without modifying other code. Using this setup, the robot worked worked perfectly, and I ended up wasting a lot of time playing. But there was one problem. When the robot moved away from the mobile, it was becoming unresponsive. Taking a look at the logs, I discovered that the robot was not actually disconnecting from the app. It was just becoming unresponsive. After digging further into the issue, I found out that the robot's Bluetooth data buffer was getting full. When the robot was near the mobile, the Bluetooth data transfer was fast, emptying the Bluetooth buffer faster than it was filling up. But when it moved away, the connection slowed down and the buffer was getting full, crashing everything. To solve this, we simply reduced the sensor refresh rate. This simple fix did the trick and everything was working seamlessly again. To make the app more fun, Carl suggested we add this cool animation. I have to admit, it looks super cool, but it was a complete nightmare to implement. First, I built the animation using an MP4 video, which I played and paused as the robot turned. But after some use, it was crashing the app. It turns out that iOS and Android devices don't like it when you have a lot of videos in an app. So I decided to replace the video with an image sequence. This looked good, but it used a lot of space in the app. The total app size needs to be as small as possible for faster downloads. So I decided to build it from scratch for the third time, this time using live 3D rendering. The result was a smooth animation, but to get a detailed render of the robot, once again it was taking too much space in the app. So for the fourth time, I decided to build this animation from scratch. The best option so far was the image sequence. After playing around with the images and converting them to WebP, I finally managed to get their size to a size similar to the MP4 video. This was excellent and it worked flawlessly, but converting all those images to WebP took a lot of time. So this actually inspired me to create my own macOS app to reduce the file size of images faster. The app is called TinyFast and it's available on the Mac App Store. I will leave a link down below. The last feature left to implement was the wireless firmware update. This would allow the robot to update itself in the future when new software is released. To do this, we needed to implement what is called a bootloader on the robot itself. A bootloader is a program which is able to change the device firmware, including itself. This is a very dangerous task because if the app crashes midway, it could break the robot, making it just a nice paperweight. To prevent this from happening, Carl decided to sacrifice the robot device memory and divide it into two partitions. The firmware is downloaded into one partition and only when it's fully transferred to the robot and verified its use as the main firmware. If something fails midway, the robot still has the current firmware intact. Coding a bootloader is not a simple task. Luckily, we found this library that saved us a lot of time on the Arduino side. The library didn't provide source code for the Android or iOS side, but it had source code for a web app which I used as a logic reference to build my own Android and iOS firmware update feature. We iterated through several designs and wireframes, and at the end, the one that stuck was this. When you open the app, you get a grid with all your robots. You can add a new one, and when you connect to your robot, the screen allows you to control it. In the top section of the screen, we have the sensors like this compass that indicates the robot's direction. Underneath this, the app shows the current movement state of the robot with this animation. We have some control switches which toggle sensors on board the robot, and in the bottom part we have this joystick which allows us to control the robot. But if you want, there are more advanced options that automate the robot's movements. When we started, I thought that this project was going to take something like a month, but on and off it ended up taking 2 years. In the end, I'm very proud of what we were able to achieve. We are already testing new devices on the app which will be rolled out very soon. If building robots and hardware is something that interests you, go check out Carl's video on his channel. I will put a link down below.